Jai Hind, I am Madhup Agrawal. Today's our topic is CPU scheduling. So, as we know, in the operating system, there are many processes. So, to keep proper tracking and engaging the CPU, there are many processes kept in the RAM and we need the CPU scheduling. Before the CPU scheduling, we can understand the some other terms that is required for understanding the CPU scheduling nicely. So, first is process control block. This is also known as the PCB. PCB, what is PCB? Each process represented in the operating system by a PCB, also called task control block. Means there are many processes. How to recognize this is a particular process and what are the properties of this particular process? This can be done with the help of the PCB. Actually, PCB is the data structure. PCB data structure for each and individual process that stores the information about particular process. So, mainly a data structure which keep the information about process known as the PCB. So, this is the information is also called the context, in for which context a particular CPU is working. So, this is known as context and this information is required by the CPU while executing the process. It contains many pieces of information associated with a specific process which are called attributes of a process. Means each process have some attributes. These attributes may be like, means each process have its unique number that is known as process ID. Program counter, this is also known as PC. Program counter means the next instruction to be executed indicated by the program counter. Next attribute of the process is the process state. There are many states of the process, means what is process is doing. We will see later. There are different process states. This is in the executing state, in the waiting state, in the ready state. There are many different states. So, this is indicated with the process state and each process have the priority associated with this. So, we must keep the track for the priority and keep the information for priority in individual process PCBs. And different registers are there. This is general purpose registers. Need to keep the track of what is going on. So, general purpose registers are there and list of open files, list of devices associated with particular process. So, all the information is associated with the process is kept in the data structure and this data structure is known as the PCB. So, means we are dealing with process, means we are dealing with the PCB also. Now, when some process is executing and we want to execute another process, then in between what is going on, means stop one process and execute the another process. Then this is known as the context switching. So, switching the CPU to another process requires performing a state save the current process. Means a process is executing and we want to stop the process and then after some time want to resume. So, resume from where? From the current state where a process process was running. So, we need to keep the current information saved to the PCB, individual PCB. So, first save the current process information. Different informations are there and these information are saved in the particular process and state restore of different processes. We want to keep another process. So, information regarding this process is loaded into the CPU. This task is known as context switching. So, this figure depicts the context switching scenarios. So, just look at this figure. Let the process P0, the process P0 or P0 is executing currently by the CPU and some interrupt or system call is there to stop the process P naught. So, what to do? First save the state into PCB 0. PCB 0 is regarding the process P naught. So, this saving takes some time. This saving takes sometimes. At this time, our CPU become idle. At this time, our CPU become idle. This is we can consider this as a overhead. And then after saving the state into the PCB 0, then reload the state from PCB next. We want to execute the process P1. So, reload state from PCB 1. We have to reload information PCB 1, and now P1 process executes and keep executing just guess at this particular time. And some interrupts occur or some system calls. Then what to do? Again save the state for the running process. Our running process is P1. So, information regarding P1 is stored in the corresponding PCB, that is PCB1. Save the state. At this time again the CPU become idle for some time. This is again overhead, and then reload the state. Again we want to execute the process P0. So, reload state from PCB 0 and then again execute the process P0 P0. Okay. So, this is the whole scenario for context switching, how context switching take place. Now, need for context switching. So, context switching, one process stops and then load the another process. So, where the condition arise, just if some high priority process comes, then obviously stop the running process and load the high priority process. If a high priority process fall into the ready queue, there are different queues are there. So, ready queue means ready to execute. So, a process with the high priority comes to execute, the current running process will be shut down or stopped by the high priority process to complete a task in the system. One of the requirement for context switching. Another requirement for the context switching is if the running process requires some input output operations, need some input output resources, the current process will switch by another process to use the CPU. If current running process require input output, then there is no need to execute the process and CPU become idle. So, we don't want to CPU become idle, then what to do? Load the another process at that particular time. And when the input output requirement is met, the old process goes into ready queue to wait for it execution by the CPU. And third requirement, some interrupts, as we have seen, some interrupts occur, then running process will stop and new process will load into the CPU. So, some requirements are there for context switching. Now, we can understand different process states for a particular process. These states means statements running process at which condition. So, there are 7 conditions, means a process can be in the new state, means just arrive, ready, and ready state, running state, termination state, and wait or block state, suspended ready and suspended wait state. So, in the figure clearly illustrated, some process arrives here, ready to arrive, want to execute, then state is new. This is generally in the secondary memory, the new state loaded into the RAM to execute. This comes into the ready queue in the queue format. In the ready queue, this is in the RAM, this is in the RAM, ready queue is there. Now, our process executes one by one. If there are n number of process, so choose the process from this particular ready queue and load into the CPU for running the process. Okay. So, this task is done by dispatcher. Selection is done by the scheduler. Two programs are there, schedulers and dispatcher. Selection is done by the scheduler. which process want to scheduler, and dispatcher loads the program into the CPU, means the context switching performed by the dispatcher. Now our process is in running state, then what can be achieved? If the process completes its execution, then termination state will be there. If process blocked or stopped due to some reason, this reason may be input output request may be there. So if the input output request is arise, then comes into the wait or blocked state, process comes into this state, means again PCB, so context switching will be there and PCB update will be done. Another reason to stop the process is some priority process comes or some time quantum expires, just in the we have discussed previously in the previous lecture. Time quantum is used in the time sharing systems. So maybe there is no need to come for input output process, just go into the ready queue directly from the running state to ready state. Okay. So this now suspended wait and suspended ready are two additional states which are used when there is no space for a new process in the RAM. So what to do? Some processes are swept out into the secondary memory, and when there will be the space in the ready queue, then swap in to the ready queue. So this is known as the suspended ready state, and our process is in the waiting state, and again goes into the secondary memory, swap in swap out. If the process is in wait state, then suspended wait state will be there. So there are different 7 stages of a particular process according to. Now scheduler. There are different schedulers, mainly long term scheduler, short term scheduler and medium term scheduler. So what scheduler does? Help the scheduling the process in various ways. We have seen there is a scheduler. What scheduler does? Choose the process for running. So long term scheduler, short term scheduler and medium term scheduler. Long term scheduler, just in the figure, many processes want to come into the RAM. So choose the process among these is the task of a scheduler, that is known as long term scheduler. So long term scheduler will work here at this place in the secondary memory. Now many processes in the ready state. So one process want to execute, one process we want to choose. This chosen work is done by a scheduler, that is known as short term scheduler, and this is known as long term scheduler. This is known as short term scheduler. Long term scheduler also known as job scheduler, and short term scheduler is also known as CPU scheduler. So choosing the process. Now where to choose another process? Means if there are no space in the RAM, so for keeping the space, want to swap in, swap out the process. So choose the process for swap out. How to choose the process for swap out? This is the task of the medium term scheduler. This is the medium term scheduler. So there are 3 types of scheduler: long term, short term and medium term. We have seen this is also known as long term scheduler. This is also known as job scheduler. Process from the pool or secondary memory, means in the new state, keeps them in the ready queue, maintained in the primary queue. Yes, we have seen already. And short term scheduler, this is also known as CPU scheduler, selects one of the job from the ready queue, selection from the ready queue and dispatch for the CPU for the execution. And medium term scheduler swap out the process from the main memory to secondary memory to free up the main memory when required. So these are the different schedulers. Now the time related, various times are related to the scheduling. or process. This is arrival time, waiting time, response time, brush time, completion time and turnaround time. Arrival time means arriving time of the process, sorry. Waiting time, how much time the process is waited for the execution. This is waiting time. Response time means after coming into the ready queue, how much time, after how much time the process start execution at first time, means difference between arrival and first execution, that is known as response time. Brush time, how much time executed in the CPU, that is a brush time, and completion time is the last point where the completed the process. And turnaround time we will see the turnaround time. Just here, arrival time is the point of the time which the process enters into the ready queue. Waiting time is the amount of time spent by the process waiting in the ready queue for getting the CPU. This is the formula is here. Waiting time is turnaround time minus brush time. Now response time is the amount of time after which a process gets the CPU for the first time after entering the ready queue, and this is calculated by the time at which process first get the CPU minus arrival time. Now brush time, amount of time required by the process for execution on the CPU. It is also called execution time or running time. Now the completion time is the point of time at which a process complete its execution on the CPU and takes exit from the system, also known as exit time. Now turnaround time is the total amount of time spent by a process in the system. How much time? System spend its time for execution and for waiting. So turnaround time is the total amount of time, means brush time plus waiting time, or we can also calculate by this formula. Completion time means we can see at CT minus this is arrival time, means AT. So CT minus AT, or we can use BT plus WT, waiting time also. Now CPU scheduling. Two types of CPU scheduling are there. First is non-preemptive approach, non-preemptive scheduling. Non-preemptive scheduling is used when a process terminates or when a process switches from running state to the waiting state. Okay, non-preemptive. And the preemptive scheduling is used when a process switches from running to ready state or from waiting state to the ready state, or we can say when preempt doesn't stop in between for during the execution is known as non-preemptive, and when it stops the process in between the running state, then that is known as preemptive scheduling. So there are various algorithms which are used for operating system by the operating system to schedule the process on the processor efficient way, that is FCFS scheduling, first come first serve, SJF, shortage of first, SRTF, shortage remaining time first, round robin, RR, priority based non-preemptive approach, and priority based preemptive approach, and multi-level queue. This FCFS scheduling, what FCFS says, this algorithm says, means first come first serve, which the process arrive first will execute first. If a process started running, then first complete its running, complete execution, and then another process will allocated to the CPU. This is the approach by the FCFS scheduling. Now the SJF, shortage of first. If there are many processes are there, then the process which have smallest running time will execute first. This is the SJF. Means in the among the available processes, the process which have smallest running time or burst time will execute first this approach of SJF. Now, another variation for SJF is SRTF. SRTF means shortest remaining time first. In this scenario, we will consider the remaining time of the running process. Remaining time of the running process. When a process comes in the RAM, then we will see the total running time of the newly arrived process and time remaining time of the current running process, which is less, then we will run the lesser process. Means we can stop the running process having longer time than the shorter process of newly arrived process. So, this is the approach for SRTF. Round robin, this approach is used for time sharing system. Round robin means we can allot a particular time, that is called time quantum. We will allot a time to the process, and after that allocated time, or when the process expire, which comes before, we will context switch the process. We will leave the CPU and allocate the CPU to another process after the certain amount of time. Means maximum time a process can execute, that is a time quantum time. Now, priority based non-preemptive priority, we have seen the each process have some priority. So, on the basis of that particular priority, we want to execute the process, means that is the priority based approach, and this priority based approach can be a non-preemptive or preemptive approach. In the non-preemptive approach, when a process allocated, then it completes its execution, then leave the CPU. In the priority based preemptive approach, priority, if a running process is there and a new process arrives, and arrived new process have lower priority than the running process, higher priority than the running process, then running process will stop, and the CPU will allocated to the higher priority process. This is priority based approach. And in the multi-level queue approach, there are multiple queues are there, and each queue have different CPU algorithm in this, and when the higher queue have no process, then the lower queue will execute its process. So, we will see. So, we can take the example to solve our concept or solve the questions to clarify the concepts. Just take here. There are different process P1, P2, P3, P4, and let the arrival time is 0, 1, 2, 4. This may be any time unit, millisecond, microsecond, or something. We can say 0 time unit, 1 time unit, 2 time unit, 4 time unit, and the burst time duration of CPU needed is 4 time unit, 3 time unit, 2 time unit, and 1 time unit. So, we can get how much waiting time, extended is average waiting time, how much turnaround time is there, or average turnaround time, means CPU different criterias, response time, what was the response time for the process, or average response time for the process, different criteria. We will see by using different algos. First by using FCFS. Just see. Before solving the process concept, we will first make the chart, that is known as Gantt chart. So, Gantt chart means a chart related to the time. So, if we are using FCFS, now first FCFS approach. FCFS, which type of algorithm is this? This is preemptive or non-preemptive? This is a non-preemptive approach. So, just Gantt chart. We are making a Gantt chart here. See, this is at the time 0. Now, this is Gantt chart. Gantt chart. At time 0, how many processes are there in the ready queue? Only one process at time 0, that is having brush time 4. So, allocate the CPU for the to the process P1 and execution start till its termination. So, total execution time will be 4. Now, at this point, how much process are in the ready queue? This process also arrive at particular this point, but we are not executing, but this particular process P3 also arrived at this point, this P4 also arrived at this point. So, at the time 4, all the processes are available, process P3, P2, P3 and P4 all are available in the RAM and ready to execute. But how to choose? How to choose which process will chosen? By the scheduler, CPU scheduler. So, we are using FCFS approach. So, first come first serve. Among these 3 processes, this process comes first. So, execute this particular process, means process P2 will be executed, allocated to the CPU and executed. The time unit is 3, 4 plus 3 equal 7 at the time 7. Now, this is terminated, this is terminated. Now, 2 processes are in the RAM P3 and P4. Now, choose according to its this approach, first come first serve. So, choose the process P3. Now, choose the process P3 and for how much execution time? 2 time, means up to 9. Now, this comes into the termination state. Now, only one process, that is P4. Now, execute the P4 process for how much time? 1 time unit, means here 10. No need to consider this one. So, this is the our Gantt chart by using FCFS approach. Now, find the different parameters, just waiting time. First, completion time. Completion time for process. We can write here completion time, total completion time. So, completion time of P1 completed at the time 4. Completion time for P2, that is 7, P2 completed the 7th point. Completion time for P3, that is 9, and the completion time for P4, that is 10. So, next criteria is waiting time. How much waiting time is there? So, how much waiting time? How much waiting time? We have already seen the waiting time formula. Now, waiting time we can calculate by using turnaround time minus brush time, total waiting time, and turnaround time equal brush time, completion time minus arrival time, completion time minus arrival time. So, first calculate the TAT, get easy. So, the TAT formula is here CT minus AT. Now, calculate TAT first. Now, TAT is completion time minus arrival time, means total time, how much time it remains in the CPU, that is TAT. So, completion time for process P1 is 4 and arrival time for P1 is 0. 4 minus 0, that is 0, equal to 0. Now, 7 minus 1, arrival time is 1, means process P2 complete at this point and comes at this point. So, the duration is this, means at this duration the process P2 remains in the system or in the CPU or in the RAM, but remains in the system. So, the TAT is 7 minus 1 equals 6. Now, this is 9 minus 2, 9 minus 2, this duration means 7, and 10 minus 4, that is 6, means at this. Now, calculate the WT, waiting time. Now, waiting time, we have seen waiting time. Waiting time means the system, the process in the system, that is TAT, and if we minus the burst time, if we minus the burst time, means minus the burst time, we can get the waiting time. Burst time is the CPU time, means how much time the process remain in the CPU, and if we minus it from the time in the system, that we will get the waiting time, total waiting time. So, this is this was 4 minus 0, this was 4, this was 4, 4 minus 0 was 4. Now, 4, this is 4, TAT is 4, TAT is 4, and BT, TAT is 4, BT is 4, 4 minus 4 is 0, means no waiting time for P1. P1 just comes into the RAM and allocated to the CPU, means there P1 does not wait to get CPU. Now, waiting time for this one, 6 is total system time, turnaround time 6 minus this burst time, that is 6 minus 3 equal 3, and this is 7 minus 2, that is 5, and this is 6 minus 1, that is also 5. So, this is the waiting time for different process, means P2 allocated to the CPU here and comes here. So, how much time in the waiting for the to get CPU, that is 4 minus 1, that is 3. Also in this scenario we can say, and P2 comes where? P2 comes at this point and exited from the system. P3 get the system at this point, means 7 minus this particular 2, that is 5, and P4 get the CPU at this point and comes at this point. So, 9 minus 4 also, this is 5. We can calculate by using another formula. So, we can also calculate the averages of this one, average CT, average TAT by summing and dividing by the number of processes, that is 4. So, summation is 4 plus 6, 10, 17 and 6, 23 upon 4, and the average waiting time is 5, 5, 10, 13, 13 by 4. Okay. So, calculate, and in the number of time units is there. So, today we will see this FCFS approach. In another lecture, we can see different approach by use and calculate these parameters, waiting time, turnaround time. Response time is also there. So, response time is for P1. Response time for P1 means 0, not to wait, response time, and for P2 again the same, waiting time comes here and get the CPU here. So, 4 minus 1 equal 3. In this scenario, in the non-primitive scenario, this is just like the waiting time, but we can see in the primitive approach this is different from the waiting time. We can see further in the different algorithm, primitive algorithm, just like primitive SGF, that is shortest remaining time first, and in the round robin, that is also a primitive approach. Okay, for today this is sufficient. Okay, thank you.